and go. So I'm going to give a short talk on quite a broad topic, 21st century changes in Antarctic and Southern Ocean surface climate in CMIP6. But I'm going to keep it short by focusing on a couple of aspects that we've been working on in our group and a couple of things we have planned. And at the end, I'm just going to show a little summary of current literature that might be handy in terms of looking at other work that's in this space. Since there isn't time for a full overview talk. Many of the plots I'm going to show are from a couple of papers that have had many contributors listed below. And so thanks very much to them for contributing. And these were submitted as part of an effort for working with towards CMIP6 papers. So my spacebar advance isn't working, so I'll use. Oh, there we go. So the first main headline result that I'd like to mention is that a major change in the CMIP6 models that we've seen compared to the previous generation CMIP5 is an improvement in one aspect of the representation of the westerlies. These are the near surface westerly winds that blow around Antarctica, which I don't really need to explain to this audience. So the plot on the left shows the latitude of the zonally averaged westerly winds in CMIP5 compared to CMIP6, and each cross is a different climate model. And then the vertical lines are the averages from in the blue CMIP6 and the red CMIP5, and then the dashed line is reanalysis data. And the headline point is that on average, the CMIP6 models are much closer to the reanalysis data. This is for annual mean, but you see a very similar thing for other times of the year. And this seems to include an improvement in the processes within the storm track. So one example is this diagnostic called the SAM decorrelation timescale, which gives an indication of the variability of the southern annular mode, which in general the timescales are too long in models compared to reanalyses, but CMIP6 is getting closer. Although it doesn't seem to have quite, there still seems to be some sort of systematic bias in this compared to the latitude of the jet, which is actually almost seems to have gone away. So that it looks like there might be still some process issues in the storm tracks, but we don't fully understand that yet. And then if we look at projections of the future change in the westerlies, something I'm just going to try and touch on is implications of the improvements we've seen in the baseline climatology for these projections. So to start with, these plots just show mean zonal wind by latitude, and these are projections of changes for different seasons. So on the left here, we've got change in zonal mean 850 hectopascal wind over the 21st century across different scenarios in CMIP6. And then that's for the Southern Hemisphere winter. And the main point here, I guess, to take home is, unsurprisingly, there's a big range across the different scenarios, with the highest forcing scenarios showing increases in the westerlies, and these actually represent poleward shifts as well, although you can't quite tell from these plots where the baseline is, but in both seasons. In the summer season, in the low emission scenario, there is this decrease in the westerly components of the winds associated with recovery of stratospheric ozone, so that the plot here on the right shows the early and late parts of the century split up. So if you look at the early part of the century in summer, there's not there's quite a lot of global warming still happening even in that low emission scenario. So you have the competing effect of stratospheric ozone recovery and greenhouse gases offsetting each other, but later in the century, the recovery of stratospheric ozone tends to dominate. So you see this effect coming up more later in the century, in the summer. Weakening westerlies and slightly equatorward shifting. I mean, these aren't in themselves very surprising. It's kind of what we saw for CMIP5. What might be interesting is, how does that compare to CMIP6? And there's qualitatively things are reasonably similar. So, in summer, if you look at this jet latitude index, you see a slow poleward shift of the jet stream in most scenarios, but unsurprisingly less so in the low emission scenario, as we've just seen, and a strengthening in most scenarios as well. Goyal et al. 2021 in their paper compared these indices for the CMIP5 and CMIP6 model ensembles, and they found that with the smaller bias in CMIP6, there was also a difference in the projections. So if you look at, it's quite a confusing plot this, but just home in on the latitude shift in summer is a good place to start. And the light colors here are CMIP5, and the darker shading are CMIP6. And then the blue is a sort of a low emissions scenario, and the red is a high emissions scenario. So in the ones I was just showing were CMIP6, so the blue one in CMIP6 shows a slight equatorward shift in the low emission scenario in summer, and then high emission still shows a poleward shift. But the key point of their paper is that these changes are smaller than they were for CMIP5. I mean, there's some difference. It's not huge. It's still qualitatively quite similar, although I say qualitatively, there's a different sign in the low emission scenario in summer from CMIP5 to CMIP6. In jet strength, there's actually very little difference between the CMIP5 and CMIP6 scenarios. So this reduction in latitude bias seems to have affected the latitude projections and made them smaller, is the headline. So, what are the wider implications of this? One of the things we see in terms, if you look at things like surface temperature change, you can see qualitative differences in the surface temperature changes in different scenarios. There's a lot of text here, but really I think I'll just try and focus in on a couple of key things. So this is DJF, so this is Southern Hemisphere summer, change in surface air temperature across different scenarios. And if you look at absolute change, it's not hugely surprising. You get more warming in the higher emission scenarios. But if you look at this carefully, in the low emission scenario, this line doesn't change very much in terms of the changes from middle latitudes towards the tropics. So in the high emission scenario, there's clearly less warming over the Southern Ocean in these sorts of latitudes. It's less obvious in this low emission scenario. And if you look at warming relative to the global mean warming, so this is so where 1 here would be warming equals the global average, then you can see in most parts, in most latitudes, there's not very much difference between different scenarios, but over the Southern Ocean, or in this type of region, there is quite a big qualitative difference. And I mean, we haven't shown this conclusively, but it looks very much like that's associated with the dominance of the recovery of stratospheric ozone in the low emission scenarios in terms of the behavior of the surface climate changes. So you get quite a big, the sort of one approach sometimes used to look at climate changes across the planet is this sort of scaling factor, where you assume that the pattern of change is the same at different levels of global warming across the planet. But for these low emission scenarios, it's less clear that applies because you have other factors dominating. So I think that the real message here really is that in lower emission scenarios, things can behave quite differently qualitatively. That's the main message. I've been trying to catch up with the AR6 report, and one of the things that stood out to me when looking at this table from chapter 12 is how, and this table is a table looking at different sort of impact drivers across different parts of the world. This is comparing the Arctic and the Antarctic, and looking at different factors like hot and cold, wind, snow and ice, etc. Some of these aren't really relevant to Antarctica, but these colours here in this table represent sign and confidence of impacts. So you've got extreme heat, for example, here, and in most of the Arctic, you've got very strong confidence, and things have already emerged. The dot here means this has already emerged in the historical period. The point of showing this is that there's for many of these diagnostics, for Antarctica, things are quite different. So there's medium confidence of increase, for example, extreme heat, and then for wind, there's low confidence on changes in mean wind speed and severe wind storms. And you saw the spread across the models that I just showed. This, of course, is very much a blanket picture, and it really does vary depending on which part of Antarctica you're looking at. So it's maybe not very easy to encapsulate one story in a plot like this, but it serves to illustrate the remaining uncertainty and also the difference in terms of the emergence of climate changes over in Antarctica, in terms of the emergence of the anthropogenic impact on change. So really just as a motivator for some of the key issues we still face in Antarctic climate change. there's not much time left, so I'll very quickly just mention a couple of projects we're working on at BAS. So one of them is a new project focusing more on coastal winds around Antarctica, and that it started this year and it's running for 3 years, and that's looking beyond the sort of circumpolar westerlies viewpoint, but more the details of what's happening along the coastlines of Antarctica. And then, just to finish, there's lots of interesting new studies coming out looking at climate change in CMIP6 and CMIP5. So I've just left a list here, which I could probably post on Slack, but many of you are involved in some of these papers as well, including people watching now. So there's lots of other interesting things going on across different disciplines. And I will stop there and take any questions. Yeah, there's time for a few questions. Thanks very much.
Hi, Tom. I have a question first.
Thank you, Jeremy. Yeah.
I wondered, for the ocean component, I think there are higher resolution now in CMIP6 than in CMIP5. That means the ocean model can resolve or permit more eddies. Can that play a role in the weaker poleward shift of the westerly winds?
It could play a role. So particularly if it changes how the sea ice responds, but actually also the meridional temperature gradients. One reason I say that is that in past work we have found a link between surface meridional temperature gradients and sea ice changes and the strength of the atmospheric response. Interestingly, certainly sea ice seems to affect the speed of the westerlies more than the latitudes, but in any case, it could be important, but I don't know if anyone's looked at that.
Okay, thank you.
Any other questions?
I wonder if we're any closer to understanding the challenges of sea ice prediction in the Antarctic, even historical simulations of sea ice in CMIP6, if we're learning more about why there's issues in the comparison to observations and then the uncertainty in the future projections.
I think we might be getting a bit closer. So one of the things I didn't really mention it, but another thing projects we're looking at is Antarctic sea ice. So postdoc Caroline Holmes, who's been working with us for a little while now, she's been comparing CMIP5 and CMIP6 performance and projections, and there are differences that some of which seem to relate to the baseline climatology representation, but others seem to relate to the different climate sensitivity in CMIP6. And it seems by comparing the CMIP5 and CMIP6 ensembles, it looks like we're able to explain some of the differences in the projections that seem to be related to the difference in global surface temperature change, and others that seem to be related to local factors. And by comparing the two ensembles, it looks like it's possible to tease those two factors apart. So, so there's some ways that we might be able to make some progress, and I guess there are other factors that are still causing questions, so such as you know, the extent of freshwater input into the Southern Ocean, and the yeah, so the freshwater input, and then another key factor is, you know, the resolution of the models as well. I think we're getting a bit closer, but it's difficult, especially with the difference between the observed and the simulated past trends, which, even though it's a sort of a more than a 40-year record now, it's still, the internal variability is still large. But that's the challenge. So yes, in some ways, and no in others.
Tom, I've got a quick question.
Yeah.
This the coastal wind field, I think I emailed you some time ago.
Yes.
Asking about the easterlies, and so we've been looking at sort of running ocean models and perturbing them, and they do quite a bit to the ocean circulation there. So they're really important. You know, which way they go in the future, and so we've been looking a bit at CMIP6 projections, and they seem to be all over the place, and they seem to be all over the place as well in the baseline. So they're important, and they're not studied enough. So it's good to see you're also looking at the easterlies here. The question I have is, you know, what we've been looking at, say, the CMIP models versus ERA interim. Do you think it's better to go to station locations and actually, you know, not go to the reanalysis products? You know, if you sort of say, is a model good with its polar easterly field? Do you think it's a little bit, yeah, not so ideal to use the reanalysis fields? Is it better to use station data?
We're working really hard on it. I had my postdoc in here actually just earlier this afternoon, looking at radiosonde ascents from these stations and ERA 5 as well. And I think at the moment, what we're thinking is using both sources of information in combination is probably the best way forward. But he's also working with oceanographers who know a lot about the data available over the open ocean. And so the first part of the project, I'm trying to piece together available in situ observations and reanalysis data sets and work out what the best sources of information are for specific evaluation metrics. So at the moment, I would say using both, but ERA 5 actually does seem to be doing quite well.
I meant to say ERA 5 when I said ERA interim. I meant to say ERA 5.
Yeah, but we don't have a clear answer on it yet. We're working on it.
Yeah, okay, all right. Yeah. Well, I'll keep you posted what we do as well. Our focus has really just been on because it's sort of an oceanography perspective. We've been looking just at the surface winds. We haven't been going up into the atmosphere in altitude. But yeah, thank you. That's
so good. If you're looking at today, we're talking about what looks like barrier flow winds along the coast of East Antarctica, and if we can evaluate them and study them, it might help to evaluate the models and understand the projections better of these coastal features. So yeah, that's another story.
I haven't looked at it myself, but I'd suspect there'd be some biases in ERA 5 just to do that different orography, you know, how it smooths out some of the deep, you know, coastal wind patterns in the reanalysis. So yeah, station data would be great, but it's discrete, right? And so that's a challenge.
Yeah. So that's a big thing you have to be careful of is if you look very close to the coastlines, the orography can look very different in reality from the models. And when you're comparing, that's why radius on descents are really useful. But if you're interested in surface winds, it's very tricky comparing in parts of steep orography.
Yeah.
Right, it's nearly 4:30 or half past the hour. So unless there's any other, well, I think I'll say we probably should move on to the agenda of the meeting. But yeah, please post any other questions on Slack. I will stop recording here.